Good morning, everyone, or good afternoon, and in fact, good evening to our colleagues in China. It's a real pleasure today to have Dr. Andreas Möri speak to us. And Andreas is currently a postdoc in the Geoenergy Laboratory in the Civil Engineering Department at EPFL. And he's studying the feasibility of fracture thermal energy storage. And Andreas holds a BS and an MS degree in civil engineering from EPFL, and he obtained his PhD from the same university in September of 2023. So freshly minted, and so the information you're going to hear is very, very current. And in his thesis, he studied opening mode hydraulic fractures and notably investigated the influence of gravitational forces on their propagation, emergence, and arrest. And so it's a real pleasure today to introduce Andreas Möri. Andreas, take it away, please.
Thanks very much for the kind introduction, John, and hello, everyone. Thank you very much for joining today and listening to me talking about buoyant hydraulic fractures, and more precisely on how they emerge, grow, and how we can arrest them. So what you see on the left in the picture is that's a dike. So that's a geological formation. It's a magmatic intrusion. And dikes are supposed, in most cases, to propagate as buoyant hydraulic fractures. So that means it's a propagation of hydraulic fracture, which is driven by gravitational forces, a buoyancy force, how we call that. So that would be a buoyant hydraulic fracture. So that's the typical setting. And when we started investigating that problem together with my advisor, Brice Le Compion, and colleagues that are also listed in here, and it became my topic, the topic of my dissertation, we actually wanted to study why is that happening in geological formations, because we see that a lot with those magmatic intrusions. So there's dike all over the world in those magmatic settings. One very nice example at the moment might even have shown up in the media is the Iceland Grindavik intrusion, which is a magmatic dike that is actually propagating below the surface over there. So you have that in that setting a lot. However, when we look at industrial treatments and at hydraulic fracturing stimulation treatments in the industry, we have no record of fractures coming up to the surface. So we have no record of that phenomenon. And the question is a bit, do they not emerge at all, or do they get arrested somewhere? And if that's the case, well, then the big question is, what's the difference between the geological formation of dikes and the industrial application where we could also have potentially buoyant hydraulic fracture? So that's going to be the framework where I'm going to go in and where I'm going to want to delimit why we have it in some cases and we don't see it in other cases. So first, I'm going to give you the basic assumptions, what's going to be in that topic or in my talk. Always one of the fundamental assumptions that we take a linear elastic isotropic solid. And that's also if we later on we'll consider maybe changes in the background stress, we'll maybe consider changes in the fracture toughness. And even when we do that, our material mechanical properties, Young's modulus, Poisson's ratio, and so on, they remain always the same in our model. We consider a Newtonian incompressible fluid, and we consider that our fractures remain coplanar at all times. So we have pure mode 1 fracture growth, where we also assume that our K1C is actually, it's only a function of space, but it will not vary with any other property of our fracture. And we also consider that it's a sharp crack tip. So it's always linear elastic fracture mechanics that is actually valid. What we also consider is that we have a block injection. So we will always release our fluid from a point source, and we start at t equals 0, injecting at a concentrate Q0 until the time Ts, when we have our shut-in. So we have a shut-in, we close the valve, we don't have any flow back that goes back of our fluid, so all our fluid remains at depth in our fracture. And one last assumption is that we have a negligible fluid lag, so we consider fractures at depth, where that's usually valid. So if we take all those assumptions together, we actually get planar 3-dimensional fractures. And that's something which, for example, Pierce and Tetourner have looked at in detail. So we got an elasticity equation, which is a boundary integral equation. and we take our mass conservation of the fluid inside the fracture, which is basically a width average balance of momentum that gives us a Poiseuille law, so the classical cubic law inside the fracture as a fluid flow. Finally, we have our propagation condition, which is, again, according to linear elastic fracture mechanics, where we simply say that we have our stress intensity factor, or the fracture energy in a sense, that is directly the same as the fracture toughness of the rock. So all these assumptions gives radial hydraulic fractures with all those conditions. We also know that very well, and it has been shown by multiple researchers, and there's a good resume of that by Emmanuel Detournay in 2016. But we see actually that we have a dimensionless toughness, where we always start from what we call the M regime, which is a viscosity dominated regime at early time. So T is small, we have a small dimensionless toughness, and we go to a toughness dominated, or K regime, in the late time. And what that represents, so what does that dimensionless value represent? Because I would like to talk today a lot about what is the physical implications of those numbers that I'm gonna throw around a bit. And in this case, it's simply a ratio between the energy we dissipate to create new fracture surfaces and the energy we dissipate to push our fluid, to get our fluid to flow in a viscous manner. And the ratio between the two, if we see that over the time of a propagation of the fracture of such a radial fracture, and the ones who followed the talk of my colleague Carlo Peruzzo 2 weeks ago, they recall this this figure, then it's a balance between those energies. So you see that here you have a blue line, which is the viscous energy, and you have a red line, which is the fracture spent to crack the rock, and the two actually cross over, and that's when we have the regime change. So it's always a bit about this energy, and it's mainly the balance between viscous and fracture energy that will dominate most of our problems. So that's all radial, and there's nothing at all that I talked about buoyancy or gravitational forces. So let's jump into that. And first, what you're going to consider, so I'll show you on the left how such a buoyant fracture could actually look like. That's oil in gelatine, and you see the opening that would be on the left. So this would be the opening, and we have the footprint on the right. But that's a late time solution. So that's already a very nicely buoyant fracture, but we want actually to know how do we get from that axisymmetric radial fracture to the buoyant fracture. And for this, we need the gravity, because that's a unidirectional force. So that will actually drive our fracture into the direction of gravitational forces. And what we might hear is the assumption that our fractures at depth, they are vertical. So the test substrate is usually such that the minimum in situ compressive stress is horizontal. So the fracture grows in a vertical plane, such that we have gravity oriented, as you see there, in the fracture plane. So our fractures remain planar, and we have gravity directly in that plane. So we make this assumption, and we make additionally the assumption that our background stress, because it's going to be related, in fact, to the overburden, it's going to vary with depth. And in particular here, we're going to say it's going to vary linearly. So it's going to vary linearly with depth. So if we take these assumptions together, that means that we actually have a gradient of stress that varies approximately with the density of the overburden rock and gravity. And if we take the net pressure, then we have in the fluid pressure, which is part of that net pressure, we have also a hydrostatic pressure. So if we take the two, and because in the flow equation, actually, it's the derivative of pressure that governs our flow and thus our viscous energy dissipation, what pops up is what we call a buoyancy strength. So the buoyancy strength as such, delta gamma, we're going to call it always delta gamma, is proportional to the difference between the two densities of the solid and fluid and the gravitational acceleration. The only thing that changes in our planar 3D scheme or in our equations is actually inside here, where we have in the Poiseuille law now an additional term, which is the buoyancy strength. And that's going to govern our problem. So we have this transition radially from toughness to viscosity dominated. But when in there is going to kick in the buoyancy? That's the big question. And for that, we first take a step back and we imagine that we have a 2D plane strain crack. So this crack is loaded by a pressure which has a component that is constant plus a linear gradient. And if we do that, and we additionally want that crack to propagate, so we want it to propagate upwards with a velocity that is above 0. To get that, if we stay in that linear elastic fracture mechanics framework, we need a stress intensity factor that equals the fracture toughness on top. And additionally, we want it to close at the bottom. So we need a stress intensity factor that is 0 at the bottom. And if we take these two assumptions, we get what is called a Workman's pulse. So in 1971, Workman has developed that solution, and it's well-defined, and it has an opening profile that we all know. And the most important is it has a length scale. And this length scale is defined as a buoyancy length scale. So that comes mostly from the magmatic volcanology community, where they look at dikes, and they define it as an LB, and it's simply a ratio between the resistance, which is the fracture toughness, and the loading, which is delta gamma, our buoyancy strength. So now, what better to do than if we have our transition from viscosity dominated, so that's going to be the blue one, to toughness dominated of our radial fracture, we have a transition length scale. But we also have a buoyancy length scale. So what we're going to do is we're going to compare the two and see what effect does that have on the change of our fracture behavior. So if we take the two, and now we have our vertices M and K, and we're going to have M and K hat. So we use the hat because it points upwards where we expect the propagation to go. So if we take the ratio LB LMK, what we get is a dimensionless viscosity. So it's again a dimensionless number, but what does it represent? So MK hat small, that would represent what you see on the left here in the blue. So that, on the right. MK hat small simply means that our LMK is much smaller than our LB, which on the other hand means that we become toughness dominated before buoyancy kicks in. On the other hand, if our MK head is big, so if our MK head is above 1, then we have the inverse case. So we're still viscosity dominated when we become buoyant. And what you already see there is that the behavior of our fracture is actually different. So if you look at LT, which is in the direction of our buoyant force, BT is the breadth, which is perpendicular to that direction. So if you look at LT, then the two behaviors are quite different. And the fact is actually that MK head captures the strength of viscous flow at the moment when we become buoyant. And that gives us two limits. So I'm going to show some videos now, because I want you to capture some features of those limits. And in those videos, what you have on the left here is actually the footprint. So that would be the black line that you see over there in that small sketch. In the center, you have the opening along the center line. So that's at x equals 0. That would be straight there through. And here you have the breadth. That would be this distance. And the length, which would simply be this distance. The color code tells you where you have the most fluid. So where your opening is the biggest. Red is where you have the biggest opening. Towards gray is where you have the smallest opening. So let's run that video. And if we run that video, what we see is that that bulk that you actually had over there, it seems to move upwards. And you also see it there. And it seems to go all the way up. So the bulk of our fluid actually remains at the top of our fracture. And when you then see that there, if you look at here, we also see that the volume there is already the same. And it stays actually constant. And in that community, that's what you call a so-called head. So we split our fracture actually into a head. And now I would like to stop. We split our fracture into a head region, which is this part, and a tail. And the head, and that's the important part here, the head is a constant volume. It has a constant shape. And so nothing changes there anymore. A direct consequence of that is that the tail has a fixed breadth. And it has also, and that's what you see in the central video over here, it also has a constant opening. So that means as long as we inject linearly at a time, then we actually get that the fracture grows linearly because there's no change of opening or volume in the tail. There's no change in the head either. So the head is at a fixed volume, and we just go propagate upwards at the same rate as we inject our fluid. That's the toughness limit. Now, if you go to the viscosity dominated limit, same setup, we still have footprint, opening at the center, breadth and length. We see that again in the beginning we're radial, but this time our opening actually has two locations where we have a bulk of our opening. We have one at the point where we actually inject in the source region, and we have one in the head. Another observation that we do here is that our fracture continues to grow laterally. So the breadth over here continues to grow. And that's not that surprising, because actually what limits the lateral growth is the fracture toughness. So in this case, we have 0 fracture toughness. So there's nothing to prevent our fracture from growing laterally. And this lateral growth actually also leads to the fact that we propagate sublinear. So our fracture slows down. That's what you observe. Also here we have a head. And the difference to the head that we have in the toughness dominated regime, in the viscosity dominated regime, is that it shrinks. So it loses volume. Our head gets smaller. And that's going to be very important later on. So the main difference is actually how much viscous resistance do we have in the head. So in the toughness dominated case, it is negligible. In the viscosity dominated case, it is quite high. And this means that that also gives us a higher volume in the head. And this difference in the volume is governing the entire propagation of the fracture. It's governing the tail. But what now if we have a small but finite toughness? And if you go into that case, then at some point we can no longer grow laterally, because we have now a resistance, which is the fracture toughness. And as soon as that one kicks in, actually our breadth starts to stabilize. So we start to stop growing laterally. So we can get for that a dimensionless toughness, we can get a time scale, and we see it actually works pretty well. And what we also see is that as soon as we stop growing laterally, we become linear in time in our vertical growth, so in the direction of the buoyancy. And that hints us towards the fact that, again, as soon as we have this condition, the volume in our head becomes constant. The breadth of our tail becomes constant, the opening becomes constant, and we're back at the case where we grow linearly because we inject linearly our fluid. Now, the interesting thing is that the volume that you get here, which is constant, is bigger than the volume that you get if you're in the toughness dominated case. And we can actually show that quite neat if we have our full space. So if you have our full space, then you see the toughness dominated limit would be this one, what I've shown you in the beginning, and the viscosity dominated limit would be the one over there. Now, in between, we have some fractures which have a uniform breadth. So from the beginning, you see that there the breadth is actually uniform. And we have the ones which stabilize. And when they stabilize, you see that they stabilize here, but then they still have a part where they actually expand or retrieve towards the head. And those one we can get the scaling. We know their maximum breadth in space and time. But the interesting thing is the heads. So all of them have a head. And all of these heads, they have a volume. And the volume from left to right increases. So the higher your viscosity, your MK head, the more viscous resistance remains in the head, the harder it is actually to propagate in the buoyant direction, the more you have a volume that you need, the more opening you actually need to generate that energy. So that's the key point that you have. Now you're going to tell me, in the beginning I said we see it in geological formations, but we don't really see it in industry. So one reason is because industrial applications, their MK head is rather situated where you have the center one, a uniform breadth, whereas dikes, so the geological formations, are rather situated in the viscosity dominated regime. That also means that we have a higher viscous resistance in the head, and it's, again, the head which will dominate the entire propagation of the friction. So far, so good. We're still injecting. We inject our fluid, but that's not really what's happening in real cases. So in real cases, what we do is we stop our injection. And that's what I'm going to talk about now. So what if we stop our injection? So our volume is not infinite, we have a finite volume. And what you see here is actually experiments that have been done in Santa Barbara in California, where you see that the fracture grows and then at some point it actually stops growing because it has a finite volume. Now, if we look at that finite volume, and we said it's kind of a length scale issue if we become buoyant or not, then the first question that we ask ourselves is, what happens to our fracture when we stop injecting? So neglecting buoyancy for a moment, but what happens if we just stop injecting? And what we see there is if we have, again, from viscosity to toughness dominated, but now we stop injecting at some point, then we actually see that dependent on the moment we stop, and we can capture that by the dimensionless toughness at that moment, we see either a fracture that stops growing immediately, or we see a fracture that shows some post-injection propagation. And what's that related to? That was one question that drove us actually further in our analysis. And one thing we observe if we ran our simulations and if we crunch our numbers and we get back to the energy balance is that in the end, so the final shape when the fracture stops is always the same because it's a static equilibrium. We have a finite volume and we prescribe that we meet the propagation criterion all around the fracture. That gives us an uniform net loading, and that gives us a static solution, which is always the same. So this one is actually independent of the injection history, and it's always there. So you see that the ones which are toughness dominated, when we stop injecting, they're immediately there. Whereas the viscosity dominated ones, they show some post-injection propagation, which you can characterize, but I'm not going to go into those details. But the end, it's always the same. So they look the same. But we have this post-injection propagation, and this one depends on the moment when we stop injecting. So there's a dependence on the way we get our volume. No, it's not only the volume that counts, it's the way we inject that volume that counts. And where does that propagation actually come from? And that propagation comes from, if you go back to the energy balance, it comes from the fact that we have an excess elastic energy stored in our medium. So what you see here is actually the energy. The light green is the stored elastic energy in our medium. Blue is, again, viscous flow. Red is the fracture toughness, and the other ones are not that important for the moment. So what we see is as soon as we stop injecting, which would be when you have the dashed line over here, the energy, the total energy spent or stored in our medium decreases. And it's this release of energy, because we've actually blown up our fracture, it's this release of energy that allows us to crack the rock further, to push our fluid through, and to get to a point where we reach that static equilibrium. So it's again a question of energy. And what we did here is that actually these kind of solutions, we termed them with a superscript V to say it's for a finite volume. And to see that that's actually what's happening or what could happen, we look again at that video, and now we already see the black circle. That's the moment they stop injecting. So there they stop injecting, and the fracture continues to grow. And it's exactly that post-injection growth that we see, and we see that the scalings actually match pretty well with what we observe. So we have this post-injection growth, and we've seen that we also become buoyant as long as we're injecting. But can we become buoyant if we have finished our injection and still grow? And the answer is actually yes. So we can also do that under some conditions, to which I'm going to go afterwards. And if you take those conditions, then we see here the video again. Again, same setup. We have on the left the footprint. In the center, we have the opening, breadth, and length. And what we see now is that although we're viscosity dominated, we actually have only one location where we have a lot of volume. So it's a bit stocking, but you see that the volume there goes up, and we only have our bulk of the volume on the top over there. Now, if you look at the transition over here, so there's a rescaling, that's why you have the jump now. But you see here is that clearly that head is reducing its size. So it's again losing volume. And in this case, because we're again zero fracture toughness, it's what we expect actually to happen. So we lose again volume in the head. And here we also see that our lateral growth, so the breadth, it stops growing. And here it doesn't stop growing because we have a fracture toughness, but it stops growing because we don't add any more energy. We stopped injecting. There's no more energy that's coming into the system. So if we take this together, we have three possibilities to become buoyant. But now the question is, do we really become buoyant or not? And that is a question which I would say is related to that length scale that we had before, to the buoyancy length scale. So if we look at that head, then that head, we can consider it as being approximately radial. So it's approximately same length as it is in breadth. So let's do that. And now I'm already going to take in a comment of Ed Sieberts here. if at the bottom we really impose that K1 is 0, we can impose K1 not 0, but just smaller than K1C, the result is the same. So that's exactly what we can do. But we can also impose it's 0, the result wouldn't change there. So if you look at that now, and now we say it's a 3D problem. It's not a 1D or a 2D problem, it's a 3D problem. So I have a radial fracture. And in a perfect world, our fracture would still be radial. And we would again impose that at the top we can crack. So the maximum stress intensity factor allows us to fracture the rock. And at the minimum, we would allow to close. So if we do that, we get again our linear pressure profile that we apply on it, and the length scale is LB. But we can now solve this for the entire opening profile, which means we can solve for a volume. And it's actually a limiting volume. So that volume with a linear pressure, a hydrostatically loaded fracture, would always lead to closure at the bottom and opening at the top. Now, this volume has been found by other researchers as well. They also found out this volume. And the question is now, how does that relate to if we become buoyant or not for a finite volume release? And we have a volume and we have a finite volume release. So what better to do than to compare the two? And if you compare the two, what we actually see is that we get a dimensionless buoyancy. So it's again a dimensionless number, but this time the physical meaning of that number is quite clear. So if BKS, if this buoyancy is above 1, then we have injected a higher volume. That is the minimum for the radial fracture to propagate in the buoyant direction. On the other hand, if it's below 1, well, then we're in the exactly opposite case. Then we have not injected enough volume that in an optimal configuration, a radial configuration, we would actually become buoyant. So that should be, in a sense, our hard cut. So before we're going there, I'm going to do a small wrap up. And the small wrap up is I've thrown some dimensionless numbers at you. So the dimensionless buoyancy, that's the last one. That's this volume ratio. So the dimensionless buoyancy is telling us, do we have sufficient volume to become buoyant, or is our volume insufficient? Above 1 sufficient, below 1 insufficient. We have a dimensionless viscosity, and the dimensionless viscosity is telling us the moment when we become buoyant, what's the governing energy dissipation mechanism in our fracture. MK hat, very big, it's viscosity. MK hat, very, very small, it's the creation of new fracture surfaces. And MK hat also gives us a hint on the volume that we have in the head. Is it small or is it rather big? Now the dimensionless toughness Ks, that's the one at shut-in, that's the one related to a radial fracture of finite volume. That would be the third dimensionless number that we have. That tells us, do we have propagation radially after the moment when we stop our injection, or do we stop our fracture immediately at the moment when we stop injecting? But the three are actually related, so only 2 of them are independent. So we need only 2 to define our entire problem. And what we decide is to take the buoyancy and the viscosity. Now, why is that? So the buoyancy actually has only the volume in it. It's a volume ratio, and it does not care on how you get that volume. You can get it as we have as a block injection. You can get it at whatever rate you want. You just need to adapt your shut-in time. Or you could get it in some pieces. It doesn't matter. It's just the entire volume that counts. However, the dimensionless viscosity, it depends on the rate. So it depends on how did we get our fluid. But it has no notion of the entire volume. So it doesn't care how much we actually injected. It only cares how do we inject. So we kind of separate those two behaviors. Then if you go further down, we just take the 2. And now we play around. And the first thing that we said is if you have an insufficient or a sufficient volume. So if you have an insufficient volume, then we should not become buoyant. And what I show here is actually footprints of those fractures, again with your opening distribution, and it's footprints of the fractures the moment they stopped propagating. So if our volume is insufficient, then our fractures do not become buoyant. So that's good news, because that tells us theory works. Now we see that if our BKS is very small, then actually our gravity, we don't care about gravity, and we have a radial fracture in the end, and we're back to the solution when we had no gravity at all. The closer we get to 1, the more different shapes we see. And that's not surprising either, because we've seen that the transition from radial to buoyant between viscosity and toughness domain is quite different. So we get some different shapes. but they're still all arresting. And I don't really care about those shapes, because what I'm interested in is, do they become buoyant or not? And here we say, insufficient volume, they don't become buoyant. But that doesn't tell us yet that the BKS equals 1 is really the limit. So we need to go on the other side and take values that are above 1. And if we take values that are above 1, then all of those fractures become buoyant. So we did around 200 simulations, and for all of them, 1 is the limit. So 1 is the strict limit, and that's good news. So we don't care about our MK head. We don't care about the dimensionless viscosity. It's only the dimensionless buoyancy that will tell us if we become buoyant or not. And what you see here is actually some different footprints. And I would like for you to take a look at the first one over there. You're going to tell me that looks exactly the same as did the toughness dominated fracture during the injection. So I'm going to tell you that if you look a bit at the tail, you see that it's clearer here, and then it's a bit darker over there. That means that we actually squeeze our tail like a toothpaste. Now, if you want to get everything out, you squeeze it from the back, you squeeze everything out. And that's exactly what's happening there. But our head, there's no change to our head at all. And why is that? Because the volume of our head, that constant volume that we had already during the injection, is exactly the limiting volume that is needed to become buoyant at all. So it's our V limit. And the interesting thing is now that as soon as we stop injecting, actually the heads of all fractures which have a higher volume, so that would be of all fractures with a MK head that is larger than what we've defined before, they shrink. So their heads go back. And if you look at the second and at the fourth footprint over here, you see here already that it's kind of shrinking towards a constant breadth. And here you see the shrinkage way better. And what you see in the second one also is that the head looks quite like what's over there. And what's happening there is that all those heads, they shrink in volume, but they cannot shrink below the limiting volume, else there would be no more buoyant propagation. So actually all those heads, they shrink to that limiting volume, and then they propagate all in the same manner as if they would have been toughness dominated right from the beginning. And that leaves us with a parametric space in the end, which is a combination of our two parameters. So we have our BKS solely deciding if you're buoyant above 1 or arrest below 1, so large or small one. But if you want to really know the propagation history, what vertices does our fracture meet, how did it grow, then we need to know how we released our fluid. So we need MK head. And small release rates or slow fluid releases hint toward the toughness dominated fracture. Large release rate, the fast fluid release, they hint toward a viscosity dominated. So now you're going to tell me you see there all those colors. So what do those colors mean? And those colors, they're actually representative of paths that our fracture takes or histories that a fracture has with limiting vertex solutions. So I'm going to take as an example the blue one over there. And we always start on what you see down there on the M vertex. So viscosity dominated during the injection. So we always start there, and we have two limits. So either we arrest at depth, so we have an insufficient volume, and we're going to end up in the static equilibrium solution of the finite volume fracture, or we have this limiting solution with the head exactly at that limiting volume, buoyant finite volume. So those are the two end members that we can get. And in this case of the blue one, we actually start viscosity dominated, and then we become buoyant, and we're still injecting. And once we are buoyant viscosity dominated, we stop injecting. So we become buoyant viscosity dominated finite volume. And then with time, we transition towards buoyant toughness dominated finite volume. So that's the path we take. And all of those fractures, they take a different path. So for all of those colors, you actually have a path that is associated with it. You see, it's kind of a mess. And we're going to ask us again the question, industry, where do we stand? Dikes, where do we stand? And actually what we see when we crunch the numbers a bit is that industry is most likely somewhere in the center over there. So we have actually in the industry fractures that should become buoyant, theoretically. But we also have such that the volume is just insufficient, so you never become buoyant at all. So we don't even have the emergence of a buoyant at all. And the dikes, well, the dikes, they, in the tendency, all become buoyant. Well, we also only know of the ones which become buoyant. So they all become buoyant, and they are way more viscosity dominated. So now the question is that if I tell you we have industrial applications where actually we can become buoyant, well, why don't they come up to the surface? And that's going to be the last part of my talk. So I know it's very dense. So that's going to be the last part of my talk, where I'm going to talk about how can we arrest fractures that are already buoyant. And what I show you here on the left is a video. It's again oil and gelatine. And that's a stress jump that you have there. And actually, if we replay the video, we see that here that doesn't arrest the fracture at all. So the fracture would actually go on. I just stopped the video there. But the fracture doesn't really feel at all that there's a fracture as such. An interface, a change in properties as such. So what arrest mechanisms are there? And we thought of a bunch of them. And notably, we thought about, we could have a change in fracture toughness. And I'm going to talk a bit about that later. We could have a jump in the confining stress. So we could have a change in the stress. We could have fluid leak off. We could also have a fracture size dependent toughness, or we could have a change in the density of the solid. We could have imagined a lot of things. So we restricted ourselves to what you see here so far. And one thing that comes into play now is that that interface, as soon as we have an interface, a change of properties, that is at a certain distance from our injection point. So we did everything in a parametric space. So if you looked at that parametric space, everything is dimensionless, and we want to get something which is dimensionless there as well. So D is a distance. Our favorite distance is LB, the buoyancy length scale. So we just take a dimensionless distance, and that will actually give us the time. It will tell us when in the propagation history we will hit that interface, which will tell us what's the state of the head at that moment, which will tell us how the two actually interact. So as I already said, I'm going to talk a bit about fracture toughness today, because that's also what last week we had, or 2 weeks ago, Carlo Peruzza talked about. And I'm going to hint a bit towards fluid leak off and stress jumps. So imagine the possible distances, so the possible scenarios we could have there. And we have the first, which is basically we don't have an effect of gravity at all. So D is very, very small. And other researchers have done plenty of very, very good work on that. There's a lot that has been done on that, so I'm not going to go into that. Then they could be of the same length. So the buoyancy length and the distance could be the same. And well, that's ongoing research. So we're currently working on that as well. I saw a paper there where it's kind of a case study where it's actually like that. And then we go to see today what's going to happen if we are really, really buoyant. So if you have a really buoyant fracture, so the distance is way further away than our LB, and then we have this interaction. What do we have as possible interactions? Well, I've already shown you this video, which is an immediate breakthrough. So we don't really feel that we have any boundary there. We just pop through. Something we can also imagine is that we reach that, then we kind of spread out laterally, but we start punching through, and at some point we actually break through. So that would be a temporal containment. And finally, we can have an indefinite containment. So what you're going to see there is that actually the fracture grows laterally. They keep injecting, and at some point what they will have is they will reach their sample boundary, but they never break through. So you see the fracture is never actually pushing into that upper layer with a different stress state in that sense. And we took that and we said to ourselves, well, let's crunch the numbers. Let's take two possible scenarios and let's compare those two scenarios, one to the other. And that's what we did. So we placed them into our space. So we placed them there. They're approximately representative of hydrogel or slick water injections, but the range is big there, but approximately that's what it could be. And that's where they pop up in our parametric space. And if they pop up in our parametric space there, then we need the distance. So we get the distance, and with this, we can actually tell where during our propagation path, those fractures will hit that interface. So one of them will hit it when we are still injecting. So we're viscous dominated buoyant, but we're still injecting fluid. And the other one's going to hit it when we are buoyant viscous dominated, but we're no longer injecting. So those are the two limits that we have, the pyramid and the droplet. So if you apply that now to a fractured jump, I'm going to reuse a slide that my colleague Carlo Peruzza has shown you 2 weeks ago. What's the range of jumps that we could actually have in the industry? And the range of jumps that you see there is 1 to 5. So 1 is not interesting. So what you're going to do is we're going to take 2 and 5. So either we double or we multiply by 5. And if you do that, on those 2 sets of parameters that we've chosen, we actually see all possible outcomes. Now that's nice. So that tells us that everything is possible, but it also means that if we really want to know, should we do all those simulations? Because those simulations, they may take hours to run, and it's for one specific case at one distance, and that's not very practical. So if you're in the industry, you would rather like me to tell you approximately what do you need, is it sufficient, or will I have something that is actually buoyant? So we want to know, can we predict all of those scenarios? And to do that, we actually look at what's happening in those fractures. So we have again a video, and if you go to that video on the left, you have a footprint again. Now you have the interface. In the center, you will have the opening. On the right, you will have the length of the fracture. And if we look at that with a jump 5, that's a temporary containment. Our fracture grows. It grows up to what you have over there. And then it spreads laterally. The opening here at the center is continued to growing. And at some point at the center, we punch through and we get again our nice little head that propagates there on top. So I'm going to quickly stop the video here, and I'm going to stop it at that point. And why is that interesting? So if we look at what we actually see there, then that, it's not willing to stop. Let me just, sorry for that. So what we see there is kind of a 2D section. And this 2D section, we can actually approximate it as a 2D semi-infinite buoyant hydraulic fracture. And that's what we show here. So we show here, if we place ourselves on the fracture tip and we look at it in a moving frame, then we can get, so from the full 3D solution, we can actually get what you see here. That's the red and everything with the dot, red, light green, and dark green. But we can also get a 2D solution for that. And the 2D solution is actually quite close to the 3D solution. But the 3D solution, so running the 3D solution takes hours. Running the 2D solution takes 5 seconds, maybe. So if we look at the 2D solution, and we can actually get a limiting solution into that, so we can run that very, very fast. So if we have a measure to actually relate the two, we can get an idea of what our head actually looks like at the moment it touches, which will help us to decide how it's going to interact. And the key parameter there is a kappa, which has been defined per operant list in 2007, which is related to the velocity of a fracture and to the characteristic opening. The characteristic opening is actually the opening that you have there in the tail. That's the remaining opening in here. And now if you go into all our regimes, and I'm going to focus on during the injection in here, we can always relate that to our dimensionless values. So in the K regime, because our velocity doesn't change, does not depend on the distance, it's just a function of mk hat. Same goes if we have the M regime where we stabilize. So if you have that stable breadth again, we are again linear in time with the propagation. So we don't, our velocity does not depend on time. It's only a function of mk hat. And only in the regime where we actually non-stabilized, so viscosity dominated at all, it depends on the distance and the dimensions. So that's a lot to say. To use the framework that has been presented 2 weeks ago by my colleague, where we actually say, we make the energy balance in that head. And I told you all the time that it's energy that is important and that the volume of the head is important, and the volume in the head is actually what governs the opening that you have there. And if you take that energy balance, we move it in a moving frame, then we get all the terms that we have here: viscous dissipation, energy, elastic, and we have a term that is related to our buoyant strength. And if we plug that into the propagation condition, we can actually come up with a balance of them, or with an equality of those energies. So that again, we can apply it at the moment when we just touch the interface. And if we apply it at that exact moment, then we have a V minus. So minus is just before we touch. that is positive. So we propagate. And the resistance to fracturing, the energy release rate there is GC1 related to the toughness of the lower layer. Then we have a state 2, and we want to not penetrate into the upper layer. So our V plus, so on the other side of the interface, is actually 0. And there what we would have is the energy release rate, which is the energy release rate of the upper layer. So if you crunch that together with our propagation condition, we end up with an equation that is telling us GC2 in function of GC1 and the state of the fracture. So the state of the fracture, we can get it from the 2D solutions. And that's what we're going to do now. So if we crunch that a bit, we put it in non-dimensional form, what we end up is what you see on top. So we have our opening that is a function of this dimensionless toughness K that you have over there. And we have our ratio between K1C2 and K1C1. And now in all the limits, we can actually get when we expect it to break through immediately. So that's neat, it's math, we play around with stuff, but you're going to ask me, does it work? And what I'm going to tell you is that the limit for immediate breakthrough for the droplet is 4.36. So at 2, we should break through immediately, which we do. And at 5, we should have a containment, which we do. And for the pyramid, it's actually 2.99. So we should have the exact same behavior. And it's again what you see. So it seems to work. We run some other simulations at the moment, and we're pretty confident it actually works. So we can predict that. We can give you a scale. You give us the numbers, and you will see if you go through or not. But what about the temporary containment? So I'm going to jump a bit ahead in that video, not to overtake too much. So we have our temporal containment. So we grew laterally. And if we grow laterally, then actually what you have there, that looks a bit familiar to me. So what you see there is somewhat a PKN fracture, no? So it grows out laterally, and it has approximately a constant height. So that's what we're going to investigate now. So here we use the approach that Yegor-Dontsov has used in his 2021 paper, where we actually have this PKN fracture. We say it's a slowly varying height, actually. We don't fix the height completely. And we say we have this linear pressure gradient there. So we neglect any viscosity in that sense. But that gives us, again, the opening. So if you have 2D plane strain, that goes back to that Workman's pulse that I told you about in the beginning. And if we do that, we can actually get a PKN solution for this case, which gives us a breakthrough time, because we can get the evolution of the stress intensity factor. And once it meets the one of the upper layer, we should actually break through. But not only that, it tells us also that if we stop injecting, we can no longer break through. So we can compare the stress intensity factor at the top, at the center, where we should break through, to the stress intensity factor we're going to have when we stop injecting. And that gives us a limit for indefinite containment. So when will we never break through? You're going to ask me again, it's nice, it's math. Okay, does it work? So the indefinite containment for the drop would be 32. So with 2 and 5, we break through. Okay, works. For the pyramid would be 4.1. And for 5, we have an indefinite containment. So it seems to work as well. But now the last question is the breakthrough time. And the breakthrough time, we can predict it within a few percent. So this approach actually seems to work. Now, something we observe here is that actually a jump of 32, well, that's just insane. So that would actually never arrest one of our fractures. The one for the pyramid, that one I agree, 4.1, it's reasonable, but it's still very high. So that seems not to be a very efficient way to stop our fracture. So that's why we turn towards the stress jump, and I'm nearly at the end of my presentation. So that's why we turned to the stress jump, because we wanted to see, is that actually more efficient? And we only took positive stress jumps, and we haven't done all the development yet. So that's ongoing work to have all those limits with the PKN and all those things. But we run a few simulations, and we run simulations where we actually had a jump of 0.5 megapascal and of 3 megapascal. And we see that 3 megapascal in any case it arrests our fracture. So it's for the 2 cases I've shown you, but for basically all industry cases, that was large enough. And we dialed that down on what does it depend on? And it depends actually on the penetration depths. And the penetration depth, which would be that bad boy there, is related to the 2D buoyancy length scale. So if we compare that to the 2D buoyancy length scale, then as soon as we actually have the necessary volume in the upper layer, then we become buoyant. And that's related to the length of our head, which is about 1.7. So which would about be over there? And we see that 1 megapascal actually already is sufficient for all the cases to stop our fracture. And that's very reasonable. Left aside, we could also have leak off. And leak off would additionally stop our fracture. So there's another one which is actually quite effective in stopping our fractures. And if we then go to the conclusions, well, we'll never have one of those isolated. We'll have a combination of them. And that's most likely what will stop our fracture in the case of industrial application. So to conclude, we have a temporal evolution of finite volume buoyant hydraulic fractures. Depends on those two values, the volume ratio, dimensionless buoyancy, and the length ratio, dimensionless viscosity. The dimensionless buoyancy alone can tell you if you become buoyant or not. But if you want to know how you become buoyant or how you propagate afterwards, then you need both. For interactions with different layers, you need another value, which is the distance to that layer. And in the end, the combination of RS mechanisms will very efficiently stop all your fractures. So that's why we don't see any in the case of industrial applications, but we see it in the case of the geological formation. So thanks very much. It took a bit too long, but I'm open for your questions. Thanks very much.
Hey, thank you so much. Really interesting. We do have a couple of questions. Ed Sieberts has two. And Ed, if you're on, maybe you just unmute.
Hi, the first one's already been answered. So yeah, that's great. The second one, I was just curious about the temperature effect on density and to what extent that might perturb your results. If you could comment on that.
Yes, so we have neglected everything that is temperature so far. We also have neglected all that would be solidification and all those things. So for the solidification, we actually made a kind of an ad hoc comparison where with some very restraining assumptions, you can actually tie it to a leak of coefficient, so a Carter leak of style. And there, nothing but the solidification will anyway stop your fractures. So then it's a question of how fast you actually propagate and how hot your fluid actually is. The change on the density as such is that if you cool down, your density will actually, well, your density will most likely change. You also have all those phase changes as soon as you would be into geology. But the density change as such would only affect your delta gamma. And if you affect your delta gamma, you would actually either increase or decrease your breadth, and you would either increase or decrease the volume of your head. But in a sense, if you decrease, in fact, your delta gamma, you decrease your forcing term, which means that your fracture would actually stop if you become denser, and it would accelerate if you become less dense. That's the
thanks. I mean, it's a very comprehensive presentation. So thanks for giving it to us. It's very interesting.
Thanks very much.
And Yegor Donsov had another question, but maybe it's been answered. Yegor, do you want to unmute and
yes, absolutely. Yeah, thank you, John, and thank you, Andreas, for this presentation. I agree with Ed that it's very comprehensive. But let me kind of. So I'm looking for some sort of like engineering summary. I mean, there are a lot of equations, a lot of theory. Not everybody has kind of time to go through all of this, especially on the engineering side and petroleum side. But one thing which was really, really interesting for me is that this critical volume thing, right? So could this be this one single simple engineering calculation which would say, what in oil and gas, so if you inject more than this in certain formations, now you start having runaway fractures. And this actually is especially important, can be important for geothermal too, right? I mean, actually, just 2 days ago, we heard a presentation, at the workshop by, Mark McClure. He tried to model these things, and in Utah Forge, as I remember, correct me if I'm wrong, John, like stage 3, right, was like in granite, single fracture, no layers. And so maybe if you just pump a little too much, now you start having runaway fractures, in geothermal, and this could be a, maybe a big problem, or maybe that's what we want, right? I mean, I don't know, right? So, but this would be very nice to have some sort of kind of fairly simple engineering conclusion saying, if you inject, this much with this formation above certain volume, then be careful. Does that make sense? So
Yes.
that's a sort of a
So,
thing.
yeah. So
take away from me at least.
So that's actually the idea of why we looked at that. So we said we see it in nature, but we don't see it in those applications. And the reason is exactly that. So if I recall correctly, we also did some simulation on Utah forage, and we got the same result. So we saw a runaway crack in one of those stages. But to go back on that, actually, what is the important if you have just as a first order calculations, you calculate your limiting volume, which is a function of the stress intensity factor, your E prime, and your delta gamma. So now your delta gamma is, you would need to know the stress state that you have at depth, but usually you try to get a handle on that. So you would need to know how it evolves, but you can get it as a first approximation just from lithostatic overburden. You can get quite good approximations on that. So you only need those three parameters. You calculate your limiting volume and you see what is the total volume you actually inject. And there it's quite important to say that it doesn't matter if you inject it in one piece or in several pieces. Well, then you have the leak off that kicks in at some point, but it's assuming you have no leak off or negligible leak off, it's just you calculate the total volume you inject, you compare it to this V limit. If you inject more, you're potentially in danger of getting a runaway crack. If you inject less, you're fine.
Mm-hmm. Thank you.
Yeah, that's outstanding, and I think that those are the questions. But Yegor is right. I'm particularly interested in this from a geothermal perspective, and Andreas, I'd like to talk more. But seeing as the questions are over, I'd really like to thank you. I mean, as folks said, there's a lot of information in this presentation for all of us to digest. Andreas has agreed to record this, so this will be available on the ARMA website to, if people want to take a second look, and I certainly will. So Andreas, I want to thank you kindly, and thanks everybody for attending.
Yeah, thanks from my side to everyone. And well, if you have questions, you can also shoot me an email. I'm reachable. You can always ask me some questions about my work. I always like to talk about it. Thanks very much for having me today.
Okay, thanks everyone.